to remind you guys, remember recording with me for retakes outside class? Apparently some students haven't noticed that I've been recording some of the notes. If you're wondering where I've been putting them, I put them in the calendar. I also have a YouTube channel for the stuff. So if you go to Canvas, on Canvas in the calendar on every day, I've been updating what we've done during the day, and that's usually where I put links to the notes that we take in class and the video of the stuff we do in class. I don't really spend any time editing the videos, so if there's a moment in class where we do a practice problem for 10 minutes, you're just going to see the camera aiming at nothing, doing nothing, but it's better than nothing. So I don't really want to. I don't really get paid to edit the videos, so I'm not really going to spend that much time on it. So, you may have noticed that as there's quite a few other parts to energy that are very math intensive, and so unfortunately this unit is not as hands-on as the forces unit was. For forces unit we did the friction lab, we did Atwood's machine lab, and so you can kind of play around with some of that stuff. Even with momentum we could do collisions. Energy is really hard because energy is really hard to measure, right? Velocity is pretty easy to measure, and we can kind of calculate kinetic energy, and we can maybe calculate some of these other kinds of energies, but it's not as visually apparent as, say, momentum or forces and stuff like that. So this is kind of more of a math-intensive unit, which means that, as I've been telling the other classes, if you were able to get by not doing much of the homework for kinetic energy, or for kinematics, or forces, or even momentum, those weren't that bad mathematically. Okay, they really weren't. The work and the energy can be pretty tricky. So try to spend some time. Don't wait until the last minute to read up on it. There's a lot of nuances for work and energy. So chapter 10 and 11, there's a lot that goes into it. So here we go, energy part 2. We'll do part 3 on Monday because the rule of 3. Always have to have trilogies, right? Trilogies. That's what makes them engaging. So, I'm just kidding. So today, we're going to look at a couple specific kinds of forces. Okay, so leading up until now, last time we talked about work. And we said that work, or the net work done, is equal to a net force dotted with this direction, and that gives delta K. Now, let me take a look real quick. Let's see here. Yeah, so we did get to talk about how you have to have a force actually in the direction of the motion, right? So even though your net force may not be in the direction of displacement, only the part of the force that actually causes it to displace actually adds energy to the system. Let me give you an example of this. I mean, this may seem kind of weird. How can you push on something without actually causing it to speed up or slow down? You would think that if you add up all the forces and you end up getting the net force, that should actually cause it to speed up or slow down, right? Because we said that F equals ma. If you have a net force, you should have an acceleration. Well, remember, acceleration doesn't necessarily mean you have to speed up or slow down. You can also have an acceleration that causes you to turn. So think about uniform circular motion. In uniform circular motion, an object goes in a circle, and you might say you have tension or something like that, pulling it in. And the tension's always towards the center. The tension will always be, say, perpendicular to the velocity. So this force, even though there is a net force, and it is causing an acceleration, is not actually causing your object to speed up or slow down. It's not causing a change in kinetic energy because this dot product, the force is not in line with the displacement, right? So you can actually apply a force on something without actually doing any work, right? You're not actually adding any energy to the system. That's something that can be really confusing because it's accelerating, it's changing direction. It looks like it's moving and changing and doing all this stuff. It seems like you're adding energy to it, but you're not. Okay, you're not. If your force is perpendicular, you're not adding any energy to the system. Drew, if you had a question? Oh, yeah. So this would be like an example. Uniform circular motion is an example of a net force not doing work. Right? So it's possible. It's possible. So it's important to recognize that your dot product has to you actually have to have a net force in the direction of your actual movement. Okay, so let's look at a couple particular forces where you do have work happening and you have energy exchanging and so on and so forth. First one is gravity. Let's look at what gravity does in terms of work. How does it transfer energy? We're really trying to be able to quantify it. So for this example, we're just going to look at a falling object, free falling object. I think that will concisely describe what we're talking about. Free falling meaning the only thing that's acting on your object is gravity. Okay, nothing else. It's accelerating at 9.8, so on and so forth. Okay, so something like a ball. It's falling, force of gravity is on it. And we're going to use positive y as up. Okay? So, we're going to go through the same process as we did last time. We're going to sum the forces in the y, which is just negative mg. But again, instead of just relating it to acceleration, we want to know how it relates to velocity. Because from there, we want to figure out how its velocity is changing, and we can use some calculus with this to solve for that. Okay, so we're going to use the chain rule here to, again, instead of trying to find how velocity relates to time, the chain rule allows us to look at how velocity is changing with respect to position. Position is what we're trying to get at with energy, especially with work, because we said that work is related to positional changes, not so much with respect to time. So this will be m dv dx, or sorry, dy, dy dt. Okay. This dy dt is essentially its velocity. So we can say this is a mv dv dy. All right, and if we bring the dy over, we get something like this. Negative mg dy is equals to mv dv. Okay, so I really want to make sure you guys understand what the dy represents and what the dv represents. Okay, when we do this dv dt, when you make this ratio and we write it like a fraction and all that,